Okay, here's the introduction to Unit 3.3, which is our study of impulse, momentum, and collisions. So we'll start by simply defining what we mean when we talk about the quantity known as impulse. So impulse is symbolized with the letter J, don't ask me why. And impulse is similar to force, but there's a little more to it. Impulse is the product of force acting for some interval of time. So the units for impulse are newtons multiplied by seconds. And there's no special name for that. So we just refer to impulse as a measurement of some number of newton seconds. I should point out that this is a product of a vector with a scalar. So impulse is a vector quantity that always points in the direction, right? The impulse always points in the direction of the force. Okay, so what about momentum? Momentum is also the product of two things. And again, don't ask me why, but lowercase p is the symbol for momentum. And momentum is also the product of a scalar quantity, mass, multiplied by a vector quantity, velocity. So momentum is a vector that always points in the same direction as a velocity vector. Well, there's a link between impulse and momentum. And here's the link. The impulse delivered to any object is always equal to the change in momentum for that object. I should include vector notation on both of these. Okay, so what we're saying is force multiplied by time interval is equal to mass multiplied by change in velocity. There's something interesting you might see here. If we divide both sides of the equation by delta t, then we get a statement that says force is equal to mass times delta v over delta t. But you recognize this quantity, delta v over delta t, is acceleration. So in a way, we're just restating force equals mass times acceleration. Obviously, we're oversimplifying here a little bit. Generally, we talk about the net vector sum of the external forces is equal to mass times acceleration. But still, there's something to be noted here about the fact that the impulse momentum theorem is consistent with material we've already learned. Okay, so what are some applications of this impulse momentum theorem? Well, there's one classic problem or example in physics that says if you were to throw an egg as hard as you can, with as much velocity as you can develop, at a bed sheet that's stretched really tight at all four corners, right? You can try this at home. You can find a few of your friends or family members to take a bed sheet and somebody grab each of the four corners and pull it as tight as they can. Try this. Throw an egg as fast as you can so it hits the bed sheet, and ideally maybe do this outside on your lawn so that when the egg hits the sheet and then falls to the ground, it'll land somewhere without breaking and making a mess. And then we want to compare. This one, I don't know where I suggest you throw it, but take the exact same egg, throw it just as fast, right? Make sure that you can consistently throw the egg with the same speed every time. This time, maybe just throw it against a wall, a brick wall or something like that, right? Sounds like I'm encouraging vandalism, but clean up after yourselves. Okay, so boom, 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 boom. This thing's going to fly and hit the wall. Here's the outcome. I think you'll find no matter how hard you throw it, you can't break the egg in this case, and it'll always break if you throw it as fast as you can against a wall. So what's the reason why? Well, force is the quantity required to make the egg break. And the reason it doesn't break in case number one is because there's less force. Case number two, when you throw the egg against the wall, there's more force, so it does break. Okay, why is that? Why is there more force in one case and less force in the other? Let's think about it. The momentum of the egg, or better yet, the change in momentum of the egg in each case is final momentum minus initial momentum. In each case, the final momentum is 0 because even when you throw it against the bed sheet, the egg ultimately is going to come to rest when it hits it, and same thing when it hits the wall. So final momentum is 0, and the initial momentum is the mass of the egg times the velocity, and you're going to make sure that that's the same in both cases. All right, so there's no difference in the change in momentum in case number 1 compared to case number 2. Impulse is equal to change in momentum. So if the change in momentum for case 1 and 2 is equal, then the impulse in case number 1 and case number 2 is equal. And that might seem counterintuitive. A lot of folks would think that the impulse in case number 2, when the egg is thrown against the wall, is greater. It's the same impulse whether you throw the egg against a bed sheet or against the wall. The difference is the force, right? So here's the key to it. The bed sheet versus the wall, well, the bed sheet causes the collision to take more time. The egg first contacts the bed sheet flexes a little bit, and then eventually over a longer duration of time, the egg is slowed to 0 and then falls to the ground. Whereas when the egg hits the wall, it seems like it's in an instant. The egg hits the wall and breaks. Of course, it's not 0 amount of time, but it's a very small amount of time. So with more time and less force, you can produce the same change in impulse as a case in which you have what? Less time and more force. If the change in momentum is the same in both cases, you could have a situation where a small force acting for a long duration of time has the same effect as a large force acting for a short duration of time. Less force and more time is the bed sheet, and when thrown against the wall, because the collision lasts for less time, it's the case in which you get a greater amount of force and the egg breaks. So in layman's terms, we might say the reason why you want to, let's say, have the airbag deploy in a car crash, right? There's your head, there's the airbag, but your head hits the airbag, then hits the dashboard. You might say, well, I want my head to hit an airbag because the airbag is soft. I think what we're really saying when we say we hope our head hits a soft object is because soft objects make collisions last for more time. Whenever a collision lasts for more time, you get the same change in impulse with a smaller force. Sorry, did I say change in impulse? I meant just impulse. Change in momentum. Think about it. Whether your head hits an airbag and slowly decelerates and comes to rest, or your head just slams right into the windshield, for example, that would be awful. In both cases, your head is going to go from a speed of maybe 60 miles per hour if you drive at a casual speed on the highway down to 0. Wait a minute, in which case does your head go from 60 to 0? When it hits the airbag or when it hits the windshield? Obviously in both cases. So in both cases, your head would have the same change in momentum. It would have the same amount of impulse. The question is just whether or not that impulse comes from a large force or a small force. If the force is large, then the time interval is small and vice versa. Let's look at this graphically. Compare two graphs of force versus time. So in one case, we can imagine your head hitting an airbag in a high-speed collision, and the other case hitting the windshield. So you're driving along, you're going at 60 miles per hour, there's no force acting on your head as you're driving at constant speed. All of a sudden the collision takes place, and the airbag blows up, and your head first makes contact with the airbag. You reach some peak amount of force, and then your head starts to come off of the airbag, and eventually your head's at rest. There you have it. You're driving along at 60 miles per hour, and then your head makes contact with the windshield. The force spikes to some really large value. That collision doesn't last for much time, and there you go. Okay, so in case number one, the collision lasts for a longer interval of time, and in case number two, it lasts for a shorter amount of time, but in that case, there's a larger peak value of force, whereas in the first case, it's a smaller peak value of force. The quantity that's the same in both cases would be the area under the curve. The area under the curve of a force versus time graph is equal to the impulse. Up until now, we've said impulse is equal to force multiplied by time interval, and that's a perfectly acceptable way to write it when force is constant. But when the force varies with time, as it would in these examples, it's probably better to break up time into small bits and add everything together so that we could say impulse is the integral of a time-varying force product with a small interval of time, and each of those little bits of impulse added up gives you the total impulse.